Good morning to everyone. After two exhilarating days of foundational insights and explorations at the cutting edge of quantum technologies, today we delve even deeper into the heart of quantum science, material theory, and precision quantum experiments. We begin this day three with a series of illuminating talks from some of the most dynamic and forward-thinking minds in the field. Our first speaker is Dr. Jayashree, whose research spans the fascinating intersection of quantum science and biology. She received her PhD in 2012 from the University of Wisconsin Madison, USA, specializing in vibronic spectroscopy within theoretical chemistry. During her postdoctoral work at the University of Toronto 2012 to 2017, she expanded her expertise to include the vibronic dynamics of electronic excitation energy transfer in molecules. From 2018 to 2023, as a Ramanujan Faculty Fellow at the Indian Institute of Science, Bangalore, she investigated photophysical processes in molecular aggregates, peak non-covalent interaction in biomolecules, and singlet fission in organic materials. Her broader interest lies in understanding quantum phenomena in biology. Specifically, her work focuses on developing methods to explore cooperative behavior in weak interaction relevant to protein folding and liquid-liquid phase separation, creating fragment-based approaches to model photophysical phenomena such as excitation, energy transfer in biological systems, and studying photoprotective pathways in biomolecules. So, please join me in welcoming Dr. Jayashree. Madam.
Okay, am I visible and audible?
Yes, madam, you're visible. I'm
Okay,
audible.
thank you very much for the introduction. So let me get started. Okay, so it's really a pleasure to be part of this series of lectures organized by UGC in conjunction with Assam University to benefit the process all around the country. And it's a very nice opportunity for me to share whatever little I know and what I'm learning at the moment at at the Institute of Bioinformatics and Applied Biotechnology. So I've been in this institute for the past 2 years, and I briefly want to spend 2-3 minutes just telling you about my background. I think Tanya has already mentioned the sort of formal part of it, but I just like to convey a couple of things before I go into our topic today, which is so-called quantum biology, right? Also, just letting you know that uh, the whole time it's going to be interactive, so please feel free to interrupt me at any point, and I'm happy to answer questions right there. Okay, so I'm actually a chemist by training. So I come from a theoretical chemistry background. So during my PhD, I worked with Professor Ned Seibert, and we were developing tools to characterize the spectroscopy and vibrational dynamics of free radicals, in particular the methoxy radical. Although the molecule is pretty small, in fact, the spectrum is immensely congested and it's very difficult to assign the transitions in the spectrum. So, in fact, this molecule is still being studied, like last 25 years, and still people are trying to understand the spectra. So, it's an incredibly difficult problem, and it was very challenging to work on it. So, I learned a lot from PhD. During my postdoc, I switched to working on slightly larger systems, in particular, like Tanya said, electronic energy transfer. And this is particularly a wide spanning topic because it starts from what occurs in plants and photosynthesis as a first step in photosynthesis, and has direct applications in development of photovoltaic cells, and efficient improving efficiency in solar cells and so on, right? So all of this led to me learning a little bit about vibronic dynamics in addition to spectroscopy. So this was also very helpful in broadening my skill set. So both put together then asked me to allowed me to ask questions in other fields which are like in biology, and that was during my Ramanujan faculty fellowship time, as well as my current research interests, which uh, I've switched to working on biological systems, and this includes looking at phenomena like the energy transfer phenomenon, but apart from that, photoprotection, particularly the photoprotection mechanisms in the crystalline family of proteins, because these are the what are called lens proteins, which maintain transparency in our eye, right? So they are responsible for maintaining transparency in our eye, and because at a later stage in our life they start aggregating, and that leads to cataract. So that's the you know sort of lifelong stability of these proteins allows us to see how and do what we do, right? So the photoprotective mechanisms are pretty fascinating, and it's not yet known how these proteins manage to stay stable. Also, I have some exposure to studying aggregates, so that's something I want to do in biology as well. So these are some of the things that I'm pursuing at IBAB. And it's a very recent photograph of my group with three MSc students who work in bioinformatics and biotechnology, and yet they were interested to learn some quantum. They have absolutely no quantum background. They were still interested to learn some quantum mechanics and try to apply to a problem in chemistry. This is my first PhD student, and some interns from Kerala who were also interested in learning quantum, and these people are still doing some work right now. Anyway, so without I won't spend too much time further on my background, because as I've just said, this does span spectroscopy and dynamics, and right now I'm interested in looking at the biological systems and quantum phenomena in biological systems. Okay, but where does quantum biology sort of fit in overall, right? So now I'll sort of move away from about my group in particular, and just so I would like to switch to the topic of interest today, just quantum biology. So the way I see it is quantum biology connects to society through basically quantum technology as well as biotechnology. And recently there's been a lot of thrust into so-called quantum biotechnology, because this is asking us, can we harness organisms to actually carry out by quantum processes, but towards function, right? So really that's the thrust. And there are a few areas that I've listed here which connects the two things. One is light harvesting. As I said, again goes back to knowing why the energy transfer process in the first step of photosynthesis is so efficient, and how can we at least mimic nature in technological applications. And then molecular recognition and sensing. This is in fact a classic example of, for instance, how we smell. How we smell is actually, or it's still a mystery, right? Because our nose has so many thousands and thousands of receptors, and then it's able to differentiate very minute differences in molecules, and still we can say gradations of smells, right? How are we able to do this so precisely? And this is the ultimate molecular recognition problem. And if we understand that, we have a very good way to develop some sensing technologies. Navigation, because if we understand how birds navigate, for instance, then we can go far in terms of navigation technology. Uh, and other things like drug development and delivery and enzyme catalysis, you can sort of see some relation between the two. But as such, the discovery process is fairly elaborate, and it's still not optimal. So people try really hard, and it takes about 15 years to develop a good drug. And so a lot of the steps these days are, people are trying to optimize it, even using AI and so on. But apart from that, there is still a quantum component which is baffling people, and AI still cannot surmount it. So a lot of these have to be understood yet. Enzyme catalysis is one of the things that people are usually familiar with a lot, because it involves there's a protein, there is an active site, and they just sort of know that there is a lock and key mechanism that leads to some reactions. The overall idea is correct, but nevertheless, what is the quantumness in this process, and how does it lead to function, right? Okay, so the field of quantum biology per se actually has several sub areas. And I've been a little careful in listing down these areas because uh, one thing I should point out to the audience here is that at the subatomic scale or the microscopic scale, basically all matter will behave as quantum particles, right? So that is not what we are asking here. Everything will behave in a quantum mechanical way if you keep going down the length scale and you start making measurements of some properties. That is not what we're saying about quantum biology. Quantum biology, in fact, refers to a specific set of areas where the true quantum nature of the object, right? Whether I'll tell you what those quantum nature means. The weird quantum nature actually manifests directly as a biological function, right? So, for instance, in the photosynthesis, the first step in photosynthesis is the energy transfer process. Now, we know that it transfers energy efficiently from the outside of the leaf to the so called reaction center, where the food preparation act sort of starts. But the thing is that this energy transfer being efficient is happening or believed to happen because of what is called quantum coherence. And this coherence is not something that you can explain classically, right? This is a manifestation of a quantum phenomenon which directly leads to a macroscopic function. Because, as I said, ultimately everything behaves quantum mechanically, but the action of all this put together leads to some classical output, and then there is some property macroscopically you can see. But in quantum biology, they're interested in very specific quantum manifestations. Similarly, in bird navigation, the quantumness that I'm talking about is so-called entanglement between two electron spins, and it is really crucial to appreciate that. And I'll tell you more about mechanisms in the second part of the second talk today. And without that, we cannot explain, or so far we are not able to explain, how the bird navigates long distances over the geographical areas, right? The third area is the olfaction, or how we smell, and that also is classified under quantum biology, because this depends upon the behavior of quantum vibrations in the molecules, right? So vibrations are not necessarily quantum by themselves. You can talk about vibrations classically, right? So I can talk about a spring which is vibrating classically. There's nothing quantum about it. But these are vibrations in molecules which are quantum mechanical in nature, and that vibrations, matching of vibrational energies and all that is crucial so that we actually smell. So that's why the classification under quantum biology. Some of the other things like vision, photoprotection, or non-coherent interactions are quantum phenomena. They do happen, obviously, in any system. Quantum particles will be there in all systems, and that is true, but it's not truly under quantum biology in that sense. That's not the focus there. Okay, so I hope I have clarified what quantum biology means, and why it is called so. So I can pause for a few seconds here to see if somebody has any questions regarding this particular demarcation that I'm talking about. Okay, so looks like everybody's on board, hopefully. Okay. So the first part of today's lectures will be, first we're going to visit the key concepts in quantum biology, or reviews the concepts that are required for us to appreciate uh, the quantumness in biological systems, right? So I've listed some of these. We'll start with wave particle duality and the basic stuff like uncertainty, quantum measurement, and collapse. Slowly move on to more sophisticated topics such as density matrix, open quantum systems, right? So finally, that's what we're going to go towards. Okay. So let me just briefly go over the wave particle duality bit, because I'm sure everybody knows this topic, and I believe a lot of the professors, when you teach quantum mechanics, you would go through history of quantum mechanics, and this is a favorite topic of mine as well. And you should, I'm sure all of us are familiar, but it's just a couple of minutes, and I'm sure we'll all feel on the same page. So we would have all learned about wave particle duality and how experiments in the early 20th century established the particle nature of electrons in photoelectric effect, where only sufficiently energetic photons could eject electrons from a metal, and wave nature in Davison-Jomer experiments, right? So where electrons scattered from a nickel surface exhibited interference patterns like waves. Okay. Although we expect the subatomic particles to show this duality in an obvious way, they will show it, and larger particles or objects are not expected to show this duality enough to be measurable. So recently, a group in University of Vienna, right? So University of Vienna demonstrated the duality in an antibiotic molecule called gramicidin. So this is what I'm showing you on this slide. So here, this is actually a molecule with, let me just try the pointer options. Okay, can you see my pointer?
Yes, ma'am.
Okay. Uh, so this is the picture of the molecule. It's called gramicidin, and it is a polypeptide of 15 amino acids. Right. So it's a polypeptide of 15 amino acids, and it's a reasonably big molecule by our standards. Right. So it's by physics and chemist standards, it's pretty huge. This actually has a molecular mass of 1882 to be precise. I will be sharing references of all the papers and links that I've used in preparation of the two talks. So definitely, you can read more about this molecule in the reference. So the exact experimental details also you can read there. But essentially, the idea is that the gramicidin is adsorbed onto the so-called glassy carbon wheel, which is then picked up by an adiabatically expanding argon gas. Okay, so that's coming through this valve, and this is a short pulse high pressure valve. And the emerging matter wave, so this is actually the polypeptide matter wave, and it has a de Broglie wavelength of 350 femtometers. So imagine the length scale, 350 femtometers, and this is caught by a Talbot Law interferometer to measure the interference of the gramicidin waves. Right. So it's basically a matter wave interferometer experiment, and they were able to detect the interference patterns and show that the experimental curve can be fitted only by a quantum wave behavior, right? So they were able to see this, and this line here, red line, is the nothing but the quantum prediction, and the green dotted line here is the classical prediction, which clearly is not what is happening in the experiment. But so just to start, I started off with this because I want to say that although this experiment was not meant to provide biologically relevant information, this is an interesting starting point for us to review the physical concepts required to appreciate the role of quantum mechanics in biology. And this experiment shows that quantum phenomena can be observed in large molecules, like particularly biomolecules here, and that too, this is under non-destructive conditions and ambient temperatures. Right, so this experiment was done under ambient temperatures. So What I want to do is, given that we have just visited the wave particle duality here, I'd like to invite you to uh, basically, hold on, let me just switch to something called Menti. And are you able to see the browser screen with okay. So I'd like to invite you. So if you have your mobile phones with you, you can sort of scan this code, QR code, or let me just move the window here. You can scan this QR code to join me in a sort of quiz where I will flash a quiz for a minute or so, like just a question, and you can answer the question and we'll review the results right there. And so that's how we will just make sure that we are all on the same page regarding that concept. Okay. So I'm just going to wait for a few seconds for you to maybe take your mobile and scan this QR code. So even if one of you have scanned this, you can either raise your hand or that you have done so. So at least people who have been able to scan it and are able to see the Menti uh, account, you can just raise your hand.
Due to internet, maybe many of the people could not see. I don't know. Let them confirm. I'm not being able to
Okay.
see your screen.
You're not able to see the slides.
No, I'm
Ma'am,
not being able to
is
because
it
my connection is poor. Probably that's why.
Okay, because right now I'm sharing
is it possible,
the.
ma'am, to share the link at least so that we can back?
Yeah, if you go to menti.com, menti.com, and there is a code that I'm flashing on the screen right now.
Just
That
share the
is
link.
okay. Just a second. Yeah, just a second. So I have shared the link on the chat. If you can just click on it and see if it works. So people who are able to access it, you can give me a thumbs up or raise your hands or. So this will hopefully happen only for the first one, and the rest of the questions it will be smooth because your mobile will already be connected. So yeah, it's fine if the QR code is there. Just as long as you're able to click on the link and you see this thing, can you just give me a thumbs up? So if you see the QR code and if you see the uh, sentence saying scan the QR code to join at Menti, that's fine. So that's what I want you to see at present. You'll not be able to see the question yet.
Yes, it is visible, ma'am.
Okay, so I see a couple of thumbs up. So maybe a few more thumbs ups would be nice. Because there are 80 people, I think, on this thing, and I just want to make sure rest of you are able to see it. Okay, I think slowly it's at least helping. Okay, wonderful. Okay, so let me push this down a little bit and flash the question. Okay, so this is the first question. So please try to take about 10 to 15 seconds to look at the question and mark your answer. You will be given choices, right? So just mark your answer and then I'll flash the correct answer on the next thing. So then we can see some statistics on how many people answered which option. Okay, wonderful. So I think everybody uh, is on board. So I think most of you must have answered. And yes, this is almost there. So let's see, one or two more, few more are coming in. Okay. Okay. So as I see it, yeah, majority have answered 85, okay, 88, and then I see some update now, 79. Okay, so I hope everyone is getting the idea that, so once I flash the question, try to answer within a minute or so. Most of the questions will be pretty short and just a small test of the conceptual part. So given that the majority have answered the longer than Bramicidin, and I'm guessing there are very few people left who are still answering. So okay, so I'll just, so the answer, yes, it is the if you take a molecule of mass 721, which is less than the Bramicidin mass, which is, you know, it's a smaller particle per se, it will have a longer wavelength, right? So as we keep going to microscopic objects, our wavelength is going to become smaller and smaller. And yes, so people who have marked longer than Bramicidin is the correct answer, right? So that's good to know everybody's on board, and we can sort of move on to the next part. So I think you get the idea. So please try to sort of keep your mentee this thing alive, and as we finish each concept, we will just try and answer a quick question to be on the same page. Okay, so the second concept I want to quickly review is the uncertainty principle, right? So we know that as you go down in atomic dimensions, it is not correct to consider a particle like a hard sphere, right? So smaller the dimensions, the more wave-like it becomes. And so when we say that the electron acts like a wave, this wave is nothing but the quantum mechanical wave function, and therefore is related to the probability of finding the electron at any point in space, right? So here, if you see this, it's a perfect sine wave for the electron spreads the probability throughout all space. Just a second. Right? Spreads the probability throughout all space, and the position of the electron is completely uncertain. Right? So P here is h by lambda, and so we have only one wavelength here, and P is known very precisely. So that's the de Broglie relation. We can precisely tell what the momentum is. But then if we now add several waves of different wavelengths together, this is going to produce an interference pattern, right? So which begins to now start localizing the wave. So that means that the position of the electron, which we could not get before, it's now more precise. It's at least starting to get localized now. But this process has spread the momentum values. So it's not 1p anymore. Now you have a series of momentum values, and that makes the momentum more uncertain. So this is an inherent and inescapable increase in the uncertainty delta p at when delta x is decreased. That is the uncertainty in each of those. So continuous distribution of wavelengths, we can with that we can produce a localized wave packet, and we know that a wider spread of wavelengths contributes to a smaller delta x. Right. So this basically is important because this has implications about the energy that would be required to, for instance, contain a particle within a given volume. And for this, let's again go back to Menti and review this with a question. Right. So So look at this question now. I hope you're all able to see the second question. If the momentum is about 10 to the minus 24 kg meter per second, the energy of confinement of an electron is being proportional to p square, and then the energy required to confine the electron within the atom is going to be how much. So this will require some participation on your part, because you will have to know what is the appropriate quantity to be confined within the atom, and what is the sort of order of energy that you would expect. So I'll give you a minute to work on this, and I'll just wait for you to put in your answers. So I see that about 39 of you are able to access the Menti, but rest of the people are not able to access. Is it? Uh, Tanya, madam, maybe can help if she can ask some of the others if they are still able to, they are not able to access. So some more people are still working on it. So okay, so let's try to see. Okay, so far I see that about 11 of you have answered of the order of electron volts, 8 of you answered mega electron volts, and this giga electron volts. So just to give you a clue, is that giga electron volts is the order of energy you need to be confined within the nucleus. So you might, if you want to think of the answer again, just see if that makes sense. This is a really large energy that is within the nucleus. So what we're interested in is the confining the electron within the atom. So something to think about. Right? Okay, I'll just wait for a few more seconds for people to catch up, and then we'll move on to the next one. Okay, I don't see any more answers coming in, but the actual correct answer is the uh, for this is the electron volts, because that is the order of energy that we're looking at for if you want to completely remove an electron, if you want to ionize the atom, then you're going to apply energy of the order of few electron volts. Yes, that's the energy we're looking at. So good job to people who have gotten this. Okay, and we can move on to the next one. So go back here. Okay. So the next concept is the idea of state superposition, right? And this is another critical concept in appreciating the role of quantum in biology, right? So suppose we have an experiment like the one in figure, and I'm sure everybody has seen this double slit experiment. So I won't spend too much time on it. And what we're doing is basically electrons are being fired at the screen, and there is some kind of detector behind the screen and records the impact or basically the intensity of electrons. First, the slit 1 is closed, and then the slit 2. Result from closing slit 1 is shown in A, and the result from closing slit 2 is shown in B, right? So basically, then when we do the same thing with both the slits open, then we get an interference pattern because of the cross term in the intensity expression, right? So the thing to note is that the intensity expression now has a sum of two amplitudes or sum of two wave functions, which obviously when you square it is going to give you this cross term. So automatically this cross term creates the superposition of psi 1 and psi 2. And remember that this is true until one tries to determine which path was taken by the electron to reach the screen. But after which the state of the system basically collapses to one or the other. So the as we know, the use of this concept is actually very prominent in quantum computing. So if people, since you've already listened to some talks about quantum computing, I'm not going to talk about it at all, and I'm not expert. So this is the idea that the um, idea of a qubit, where a quantum state can exist in a linear combination of both the ground and excited states, or both the 0 and the 1 qubits, right? So this is a familiar thing to everyone. And in classical physics, I can only have one of either 0 or 1, but in quantum state, I can have a linear combination of the two. Like a Schrodinger's cat can be both alive and dead at the same time. So here we know how this can be represented in a very elegant way. This is a block sphere representation. And here the zero ket, or the zero state, is going to be along the z-axis, and the one state is along the minus z-axis. So any other point on the sphere is basically a linear combination of 0 and 1 with the appropriate factors, right? So along the x-axis, it's going to be 0 plus 1 by root 2, whereas y-axis 0 plus I 1 by root 2, and anything else just has the contributions from theta and phi for that particular point on the sphere. So this is something that also is a crucial concept for quantum biology. So here I have another question for you. So hopefully this won't take long. So we'll not spend too much time on the questions. I hope that people are able to do it more or less. And, so this is the okay. So mark your answer for this question. Which of the following is false for a superposition state? It's a very simple question, so we don't need to spend more than 10-15 seconds on it. So if you can mark your answers. There can be more than one correct answer. That also I will tell you. Yeah, I would encourage more people to mark the answers. I received 16 out of 44. So others, please go ahead and mark what you think is the one or more correct choices for this question. Some more people, some 20 people at least, have to still mark. Okay, a few more people, if you can attempt, it will be good to see some response. Okay, so what I'm seeing here is that a majority of you actually have marked a wave function can be expanded only in an orthonormal basis. And many of you have marked this thing, the linear combination of component states. So I should tell you that it's the third one is not necessarily the only thing. You can expand wave function in non-orthonormal basis as well, but you just have to be careful when you solve the Schrodinger equation. So this is commonly done in electronic structure. So you can keep that in mind while you answer, right? So I will also flash the correct answer now so that we can move on. I hope you've learned something from this question. And basically, for this part, what I would say is that which of the following is false for a superposition state? I would say that the third one is false because it is not the only way to expand the wave function. So it can be expanded in other basis as well, right? So it is, you just have to be careful in solving the equation. Okay, so that's right. So here when people mark this, these are not, it's not false. So you have to be careful about the question. These are in fact true statements. Okay. Okay, so let's move on. Right. The next concept that we want to revisit is the notion of entanglement, right? So, like any other aspect of quantum science, entanglement basically reveals itself at subatomic scales, right? So, when two particles such as photons or electrons become entangled, they do remain connected even when separated by vast distances. In other words, they actually behave as one object. Right? So entanglement arises because of the connection between the particles and not because of some information within them. So the connection is what carries the information about the entanglement. So this is, I think, a classic way of explaining entanglement with Alice and Bob. They're trying to observe the color of two entangled balls in their boxes. So we can imagine this yellow-red ball that's shown here, right? Half yellow, half red. That's present in two boxes, and this is a superposition state of 0 and 1. And if you see this now, the two of them are going to observe the balls, and they say, if minus Alice is minus yellow, so is going to be Bob's. That's also going to be yellow. But if she sees red, then he's also going to see red. So it's behaving like a single object. But the thing is that it's the tricky part is when they observe from different angles. So here the cartoon representation of a different angle basically means in a real experiment along which spin direction, for instance, if you measure a superposition spin state. So it really depends on that. So suppose in this case, Alice is going to observe at a different angle or from the side of the box. She'll have a 50% chance of being yellow, 50% chance of being red. And then she says, oh, I just saw that it was red, but it's not really. What is going on? Right. So she might find a yellow ball now. And once she sees a yellow ball, he's also going to see a yellow ball. Right. So this is this thing. So as long as they're entangled, whatever is happening to one of them, one of the particles will happen to the other. The collapse is the same. But why is this concept important? This plays a critical role in the mechanics of how birds migrate. Again, this will come up in migration of birds because this involves the entanglement between two spins. Okay, so the review part is pretty quick, and the question part is usually what seems to take time. That's okay. We'll just revisit a question in entanglement as well. Let's see how that goes. Okay, so this is so. Can we look at this question now? We consider a two-spin system, and what is the combination 0, 0 plus 1, 1? What does it produce? Do you think it produces an incoherent superposition state? Does it produce a coherent superposition state? Does it produce an entangled superposition state? There can be more than one right answer. I still see people answering, so I'll wait for a few more seconds. Okay, so I don't see any more answers coming in. Looks like 27 out of 48 have answered. Okay, and yes, so the correct answer is that there is an entangled superposition state, but it's also actually a coherent state. So let's see. So both of these are actually true in this case, and entangled is actually a very specific case of coherent state involving multiple particles, right? So we will just see this in a few seconds. So people, at least a person who has marked this also as a coherent state is correct, but it is an example of an entangled state as well. Okay. Okay. Very good. So I hope you're enjoying this part. So let's, okay, let me go back to the window. So let's, okay. So the next concept we'll quickly review is the notion of tunneling, right? So we know that according to classical physics, a particle of energy E, if it has energy less than the height u naught marked here, it cannot penetrate, right? So the region inside the barrier is classically forbidden. But the wave function associated with a free particle can penetrate. And what will happen is that because based on continuity and the fact that it is, able to penetrate the barrier, unlike a classical particle, it will show an exponential behavior inside the barrier and oscillatory behavior outside the barrier. So on all points, it should be continuous. So we do use boundary conditions to match the wave function behavior, and that's how we get this solutions, right? So I don't need to go over the basics for the audience here, but the essential sort of applications of this are throughout. One is alpha decay through the Coulombic barrier in physics, solid state physics, solid state chemistry, and more importantly in biology, it is seen in enzyme catalysis. So for instance, this is a simple figure which shows that if there are two states where the one state has a proton attached to an alcoholic group here, and the reaction should involve the transfer of proton from one alcoholic group to the other, and there is a barrier associated with the process, right? So classically, unless the molecule, the reactant, can surmount the barrier, this transfer of proton will not happen. But proton being a quantum mechanical particle, it can actually tunnel through the barrier, right? It can go through this and go to the other alcoholic group. So the thing is that here, when the tunneling happens, it's not just dependent on the height of the barrier, but also it depends upon the width of the barrier. Whereas in classical physics, what we would expect it, as long as it has the energy over the barrier, I mean, higher than the barrier, it can just go over the barrier to the product side. But in quantum tunneling process, it depends both on the height as well as the width of the barrier. And so this makes it very interesting in terms of what you expect to happen, right? So, okay. So again, I'm going to flash a question in tunneling. So let's do that. Okay. So what do we expect to see if the energy of the particle is above the classically forbidden region? So again, here you can have more than one right answer, but I'd like you to do your best in terms of predicting what happens. Okay, about 18 people have answered. I'd like and encourage more people to attempt the answer. It's not a numerical exercise, so just think of what will happen for a higher energy particle. Okay, so I see 23 people have attempted it. Okay, any more? Maybe a few more if you're interested in okay. Okay, so anyways, I will flash the answer for people who have attempted it. Yes, for the most part, the wave function is going to oscillate with less amplitude in the classically forbidden region. And because when you look at the transmitted wave, it has the same energy as the incoming wave. For the higher energy particle, the tunneling really doesn't happen, right? So it just feels the potential when it goes over the barrier, but it's not really tunneling, right? So that's the way we think about it. Okay, so I'm glad to see some of you are actively participating. So let's get back to the presentation. So go to the next concept. Right. Okay. So the next one is the idea of coherence. Right. So coherence is a well-defined phase relationship between two objects. Right. So it can, in this case, we're talking about waves. and in this case, wave functions in quantum in particular. However, we also know that maintaining this relationship is incredibly difficult, right? It's subject to disturbances, such as, if you change temperature, or if you have mechanical vibrations, if you have impurities in your material, or some other particles, or you're subjecting to electromagnetic radiation. This is going to get destroyed, right? So this is the representation of that in the schematic, where there is a well-defined phase relationship, but it just goes away once there is some disturbance at some point. And we know that the longer we can keep the coherence, longer we can store information or process information, and that's the key focus in a lot of these areas like quantum computing and quantum networks or quantum sensing, right? How long can you keep the coherence to get what you want to be done? And here, I will show you that coherences play a sophisticated role in biology, in the sense that in biology, the systems are pretty complicated, right? You have a molecule which is binding to a protein, or there's some enzyme which is catalyzing a reaction, but there is a protein environment surrounding the active site. So generally, the environment is believed to be a bad thing in terms of destroying the coherence and so on. But there is a lot of evidence recently in biology that they are actually helping and not necessarily a bad thing in biology. So this is particularly in the context of electronic excitation, energy transfer, and photosynthesis. And a lot of interest in this area is coming up because how it is helping the process and not necessarily destroying the coherence. Um, one thing I want to mention that the coherence and populations, all of these are encoded in what is called the density matrix. So all possible states that can be realized by the quantum system is part of what is called the density matrix. And this is basically what we're going to visit next. So, and before I forget, I'll give you a question on coherence as well. So let's switch to that. Right. So this is what I was saying. Now, hopefully, people who have listened to that question can mark this, instantaneously. Something I said about coherent and entangled states a few minutes ago. So feel free to mark your answers. Is everyone able to see the question? I don't see anyone marking the answers. some more answers, hopefully. Yeah. Okay. Few more people, if you'd like to attempt, I will then flash the correct answers. Okay, I don't see any more people answering, so I'll just go back to this. So just to wrap this one up, we have entangled states that exist because they involve multiple particles, right? But coherence need not be multiple particles. It is very much something that you can observe with a single particle because of the superposition of multiple states, right? All entangled states are coherent states. That is correct, but the reverse is not necessarily true because again based on the multi-particle involvement, right? So this is the first one is not there, but the other two uh, are true about the coherent and entangled states. Okay, so I'm just switching back to the presentation just to finish couple more concepts. Uh, I see some people are replying in the chat, but the way Menti works is you have to mark your answer in order to be recorded. So, if possible, try to do the answers on your mobile itself. Yeah. Okay. Okay. Very good. So, briefly again, let me just review the notion of density matrix and open quantum systems. Right. So any quantum system which is in contact with its environment, it's what counts as as an open quantum system. So when we say the theory of open quantum systems, it could essentially be a theory about everything, right? So any sort of problem can be posed in this manner with certain constraints. And mathematically, how would you describe it? You would talk about the system Hamiltonian, right? So there is a system Hamiltonian here. The pointer. Yeah. So there is a system Hamiltonian and a system density matrix associated with this Hamiltonian, which interacts with a path or an environment with its own Hamiltonian and density matrix. And there's an interaction term, HSE. Just like the Schrodinger equation, this composite system follows the Liouville polynomial equation. So that's its time evolution is dictated by this commutator. And the density matrix being, can represent all possible states of the system. What I mean by that is it can represent what are called pure states as well as mixed states, right? So pure state is something that is well-defined linear combination of the component states, and then you have a projection operator based on that. But when it comes to mixed state, all you have information about the mixed states are basically the probabilities associated with the component projection operators, and you find the averages based on the knowledge of the probabilities, right? So there's certain weights that come with it. So there is the division between what the density matrix elements represent right? So the diagonal elements represent populations, diagonal elements represent coherences. So the density matrix not only represents different types of states, but it also represents coherences and populations in our experiment, right? So that's the review with this thing. So one thing that to also mention, I should mention, is that the system interacting with the environment can be through various ways, or at least it's modeled through various ways, whether it is perturbative interaction or whether it is non-perturbative, etc. So all of these matter in terms of the way we get the solutions. Okay, so just going back to this thing question, let's review this particular concept with a quick question. Right? So which of the following statements best describes an open quantum system? Right? So read through the options and you can pick the statement that you see that it fits best. There's only one answer for this. Okay, a few more people who can attempt. Okay, we're getting about half the people attempting here. And so it looks like this question was quite easy because almost all of you, except for one person, has answered this, and it is actually correct, right? So the others are not necessarily correct because this is not an open quantum system, and this one is sort of too specific, and it's also not necessarily even talking about an environment. So here, this is the best description of the open quantum system. Okay. So So the last thing that we're going to review before I go to the applications to the quantum biology side is the notion of spin and spin dynamics. Right? So this goes way back in history, right? So there were two types of experimental evidence which came up in 1920s that suggested that there is an additional property for the electron apart from its n and that is n quantum number as well as the orbital angular momentum quantum numbers. So one evidence was the closely spaced splitting of the hydrogen spectral lines called the fine structure, and the other one was the Stern-Gerlach experiment, which showed that a beam of silver atoms, basically when it's directed through an inhomogeneous magnetic field, would be forced into two beams. Okay? So both of these experimental evidences were telling us that there is an intrinsic angular momentum, magnetic moment by the individual electrons, and classically this, if this could occur, it's as though the electron was a spinning ball of charge, and this property was called electron spin at that time, right? So it is intrinsic property of the electron. It has plus half minus half component, z component, right? And basically where we are heading with this is that we are interested in how it will interact with the nuclear spin, because nuclear spin can have sometimes magnetic moment as well, and it can have spin greater than zero. So when that happens, this gives a rise to what's called hyperfine splitting, and this splitting will be observable in techniques such as EPR, electron paramagnetic resonance, or ESR as well. And the spectral lines that would normally be single are now split into multiple lines because of the different possible combinations of electron and nuclear spin arrangements or orientations, right? So all this will come up again in the applications in the biological systems. So okay, so at this point, maybe it's a good time to give a break of about 10 minutes if Tanya is agreeable to it, and we can have a small break. And then I'll come back and we can start looking at the quantum biology part of it.
Yes, yes,
Is that
madam.